The main purpose of Euler's method is to find a numerical approximation of a solution to a differential equation when we're trying to find an exact algebraic solution is either too difficult or not possible. You can think of Euler's method as this sort of bridge. On one side, we have a formula that tells you how something is changing, which is the derivative. And on the other side, we want to know the exact state of that thing at a specific point in time. Euler's method allows us to cross this gap between both sides by using simple arithmetic. So, in introductory calculus, we often solve differential equations using integration. However, many real-world equations, like those that predict weathers or are used for predicting patterns within complex fluid dynamics, we don't have this closed form solutions. So, Euler's method provides a way to get a good enough answer using basic addition and multiplication rather than complex integration. And we say good enough because remember, Euler's method is still an approximation because we're doing more simple arithmetic as a trade-off to doing complex integration. And I think another important thing to keep in mind is that differential equations describe continuous motion throughout time. However, computers, like the ones we often use, think in discrete steps. So these are like your ones and zeros, your frames per second, right? So Euler's method allows us to break a smooth continuous curve into a series of tiny straight line segments. So by doing this, it makes the math compatible with computer processing. Um, so that's the basic gist of Euler's method and the purpose of it. Now, let's take a look at some examples to see how Euler's method is applied within actual calculus. So, in this specific problem, we're told to consider the differential equation dy over dx is equal to 2x minus y with the initial condition f of 0 is equal to 0. Use Euler's method to approximate f of 2 using four-step integrals. Four steps. Okay, so the first thing we have to note is our four steps. We understand that we're going at four steps. Now we have to know our range. So we're going from 2 to 0 over 4. This simplifies to 1 half, or zero point 0.5. Okay, now that we know this is our steps we're incrementing by, we can set up our table to approximate for f of 2. So our table should look something like this: x, y, dy over dx, and then y is equal to m x minus x, we'll say x1 plus y. Okay, so then for our x, we're going to plug in our initial condition. So we plug in 0, and in our y, again, we plug in our initial condition, and we plug these into here. So we know 2 times 0 minus 0 is just going to be 0. So we're left with y is equal to 0, x minus 0 plus 0. Okay, and then we increment by zero point 0.5. So our x goes to zero point 0.5. And if we were to plug this back into this equation, we know that if we plug in 0 here, we get zero point 0.5, but because it's being multiplied by 0, it just goes to 0. So our y value is just 0. And we can plug this into our dy dx equation, right? And we would say dy over dx. Our y goes to 0, so then it's just 2 times 0 0.5, which is just 1. So 1. Now we can set up our equation. So our slope is 1, right? Our slope we were told is 1. X minus our 0, which is 0 0.5. I'm going to write it as a fraction because it's easier to interpret. Plus 0 again. Okay. And again, we increment by 0 0.5 because we were told are using 4 steps. So now we're at 1. Okay. We can plug this x value back into here. So we're left with 1 minus 1 half, which will just be 1 half. 1 half times 1 is just 1 half. So our y value is 1 half. And now we can plug that back into our dy over dx equation. Dy over dx is equal to 2 times 1, which is going to be 2. And remember, we're using this x value now to plug into here. So 2 minus 1 half. This can be written as 4 over 2, and this is 3 over 2. Okay, 3 over 2. And then we write our tangent line equation. So y is equal to 3 over 2, x minus 1 plus 1 half. Okay, we increment by 0.5. I'm going to extend our table just a bit more. Okay, so now we're at 1.5. And then we plug in 1.5 here. Let's see. I'm going to scroll down just a tad bit. We do 3 over 2. 1.5 is the same as 3 over 2 um, minus 1. But because our denominator is 2, I'm just going to do it as 2 over 2. So it's easier to subtract. Plus 1 half. This becomes 3 over 2 times 1 half plus 1 half. This goes to 3 over 4 plus 1 half, but I'm going to rewrite it in terms of 4. So this is 5 over 4. 5 over 4. And then we're going to plug that into our dy dx. Let's see. So dy dx is going to be equal to 2. Again, I'm going to rewrite this in terms of 3 over 2 plus 5 over 4. This will be 3 plus 5 over 4. But again, I want this in terms of our denominator to be at 4. So I'm going to write this as 12 over 4 plus 5 over 4, which is going to be 17 over 4. And again, we're going to rewrite our tangent equation, which is going to be y is equal to 17 over 4, x minus 3 over 2 plus 5 over 4. Okay, again, we increment by 0.5 because that's what we calculated here. And now we have 2. And this is the final thing. Now we're close to approximating f of 2. So now we plug in 2 into this equation. So 17 over 4. Again, since I'm in terms of 2, or because I would subtract 2 within this grouping, I'm going to write this 2 as with the denominator 2. So it's going to be 4 over 2 minus 3 over 2 plus 5 over 4. This goes out to be 1 half. So 17 over 4 times 1 half plus 5 over 4. This is going to be 17 over 8 plus 5 over 4, but because our denominator is 4, it's easier to just multiply this by 2. 10 over 8, 27 over 8. And that is our approximation. So we know that f of 2 is approximately 27 over 8. Again, this is Euler's method, so this is just an approximation. This is the closest we can get to just using simple arithmetic, simple multiplication, instead of having to go through that integration process. Let's take a look at one final example. This example says to use Euler's method to approximate the value of f of 1 if dy over dx is equal to 4 parentheses x plus y squared parentheses and f of 0 is equal to negative 1 using 4 steps. Okay, again. We have an initial condition, but first we want to see our incrementing value, how much we're skipping our x values, and to do that, we should be given our initial condition. So 1 or Yes, 0. Or no, sorry. Yes, 1 minus 0 over 4. This is going to simplify out to 1 over 4. And in the previous example, we saw that using fractions, which is a lot easier than having to use decimals. Um, so I'm going to leave this as a fraction, just because it's going to be easier in the long run. Okay, now that we know we're incrementing by this much, let's create our table. So x, y. Okay, dy over dx, and then y is equal to x, m of x minus x1 plus y. Okay. Okay, now we have our table set up, and we know we're incrementing. We're starting off at 1/2. Oh no, sorry. We're starting our initial condition, which is this. So we start at 0, and then we were told that at 0 our y is -1, and we plug this into here, our dy over dx equation. So we know that dy over dx is equal to 4, and our x is 0 plus -1 squared. So this just -1 squared just comes out to be +1. So 4 times +1 is just 4. So 4, and then we can rewrite our equation: 4x minus 0 minus 1. Okay, now let's increment by 1/2. I mean 1/4. 1/4, that we plug this into here. 1/4 minus 0 is just 1/4. So 4 times 1/4 is 1. 1 minus 1 is 0. And we plug that into here. Our dy over dx equation is going to be equal to 4. Our x value is 1/4 plus 0 squared. Again, 1/4 plus 0 squared. 0 squared is just 0. So 1/4 plus 0 is just 1/4. 4 times 1/4 is going to be 1. Okay, so y is equal to 1. X minus 1/4, because that was our x value here, plus 0. And then we increment again. 2 over 4. We plug this value into here. So now we can do 1 minus 2 over 4 minus 1 over 4 plus 0. But because we know 0 won't have any value, I'm not going to write it out. So 2/4 minus 1/4 is going to be 1/4. 1/4 times 1 is going to be 1/4. So 1/4. And then we plug our order pair back into our dy over dx equation. For our x value was 2 over 4 plus 1/4 squared. 1/4 squared comes out to be 1 over 16. We can rewrite this as, because we want this in terms of 16, I'm gonna multiply this fraction by 2, or no, sorry, by 4. So this becomes 8 over 16 plus 1 over 16. 9 over 16 times 4. This would be equal to 36 over 16. 36 over 16. And then we rewrite our tangent equation. So 36 over 16. And then x minus 2 over 4 plus 1/4. And then we rewrite 3 over 4. Okay. And then we plug that back into this equation. But for the sake of this video, I'm going to use a calculator to avoid doing all the arithmetic. It's just tedious, simple simplification with fractions. Uh, and the point of this video is to teach you Euler's method, not addition and multiplication of fractions. So I'm just going to use a calculator. So again, I'm taking this x value, right, and I'm plugging that back into this tangent equation. So 36 over 16, parentheses 3 over 4, minus 2 over 4, plus 1 over 4, which gives me a y value of uh, 13 over 16. And then we're going to plug these ordered pairs back into our dy over dx equation. Again, I'm going to use a calculator. So 4 parentheses 3 over 4 plus 13 over 16 squared. And this is going to give me a dy over dx value of 361 over 64. And we rewrite this, or rewrite our tangent equation with these new values. X minus 3 over 4 plus 13 over 6. And again, now this is our final step because we're approximating for f of 1. So 1, we plug that into here in this equation. So 361 over 64, parentheses 1 minus 3 over 4 plus 13 over 6. And 1 is about 2,747 over 768. So f of 1 is approximately, let's see, by simplifying into a fraction, we get 3.5768. And that's an approximation of what f of 1 is equal to using Euler's method with 4 steps. And as you may pick up on this, the more steps you have, the more accurate your approximation is. And the less amount of steps you have, the less accurate you are. And yeah, that's Euler's method.